Welcome to section 14.8. In this section, we're going to be looking at another way that we can find maximum and minimum values of a function, but specifically functions that are subject to a constraint or some sort of restriction put upon them. So in the previous section, we did an example where we maximized a volume function, so that was v equals xyz, subject to the constraint 2xz plus 2yz plus xy equals 12, which expressed the side condition that the surface area was 12 square meters. So when we were looking at maximizing this function, we weren't trying to find the maximum of the entire function because unrestricted, it doesn't have one. This will grow as x, y, and z grow. This grows infinitely large, and it will never stop growing. It doesn't have a maximum by itself, but the material restriction, that constraint, told us you only have 12 square meters of cardboard to work with. Subject to this restriction now what is the maximum of this function? Okay, so in this section, we're going to talk about Lagrange's method for maximizing or minimizing a general function, that's f of xyz, subject to a constraint of the form g of xyz equals k, or in other words, a constraint that lies on the level curve g of xy equals k. So I want to try to visualize this a little bit. So I've got a graph down here for us to look at. So we're trying to find extreme values of f of xy subject to a constraint of the form g of xy equals k. So for this example, take f of xy equals c with level curves 7, 8, 9, 10, and 11. So you can see that's all the red curves here. So these are all different level curves of some surface, some function. Find the largest value of c such that f of xy equals c intersects with g of xy equals k. So the red level curves, these are all the possible values for the function, right, on these different heights. G of xy equals k, this is the constraint. This is the restriction that's cutting across our function. Now, we're not saying to find the maximum of the function as a whole, because as you can see, these values are increasing. We get a value of 11 up here. We don't even know what happens beyond this. It could keep growing. So there doesn't appear to be a maximum anywhere in here for the function. But when you introduce this restriction, we see this cuts through the level curve here at 7, and it settles in until it hits this point right here on the level curve of 8, and then it dives back away from the level curves again. So the highest output of the function, the maximum output that is also on g, is right there, and that's a value of 8. Okay, so in this hypothetical example, the maximum of f subject to the constraint of g equals k would be 8. Okay. Now, how can we find this mathematically or analytically? Through the method of Lagrange multipliers. So to find the maximum and minimum values of f of xyz subject to a constraint g equal to k, we're going to find all values of x, y, z, and lambda such that the gradient of f of xyz equals lambda times the gradient of g of xyz. We're going to find all values of x, y, z, and lambda such that grad f equals lambda grad g, and g of xyz equals k. All right, so we have this relationship, grad f equals lambda grad g, and the constraint itself, g equals k. We're going to find all values that satisfy these. Okay, so in other words, we're looking for ordered triples, x, y, z. And then once we have those, we're going to evaluate f at all of the points that we found. the largest is the max, the smallest is the min. So it's more similar to the idea of working with the absolute extrema that we saw in the previous section. Lambda is called a Lagrange multiplier. So lambda, that Lagrange multiplier, is giving us another tool that helps define this relationship. And lambda, when we're solving these problems, lambda sometimes will become very, very important to the solution. We might have to find lambda in order to find x, y, and z. Other times, lambda might not be very important at all in the solution. We might not even need it, and we just kind of work past it to get to x, y, and z. Every problem is different. The setup and the procedure for every problem is different. So as long as we have this initial relationship defined, the process can look different from problem to problem. So let's take a look at our first example. This is the same example that we looked at in the previous section. So a rectangular box without a lid to be made from 12 square meters of cardboard. Find the maximum volume of such a box. So we found this last time. We're going to show this result again, but now through the lens of the Lagrange multipliers. So we have V equals XYZ subject to the constraint two xz plus 2yz plus xy equals 12. So we want to look for values of x, y, z, and lambda such that grad f equals lambda grad g, and g of xyz equals 12. So we'll always know what the constraint function is because the constraint function is the one that's being set equal to the constant. In this case, that's the 12. And now if we want to solve this, so grad f equals lambda grad g, we know that the gradient vectors are just vectors whose components are the partial derivatives, right? So in this case, actually, let me call this grad v, just so that we're consistent, because I'm calling this function v here. So if grad v is equal to lambda grad g, then that means the corresponding components will be equal as well. So in other words, vx will be equal to lambda gx, vy equals lambda gy, and vz equals lambda gz. And of course, the constraint is just this equation again. So we have three equations from grad v equals lambda grad g. And then we have the constraint. All right, so if we go ahead and get these equations now. So we have Vx equals lambda gx, so Vx is going to be yz equals lambda times gx, that's going to be 2z plus y. 2z plus y. If we go to the partials with respect to y, we get xz equals lambda times 2z plus x. And if we go to the partials with respect to z, we get xy equals lambda times 2x plus 2y. Now, if we take a look at these equations, our goal is to find any ordered triples, x, y, z, that we can then get out of this system. So we need to solve this. We can do this via many different methods. The one that I'm going to show you right now is not necessarily the only way to do it. This is just the one that maybe I noticed first, or that just seems the most straightforward. There's usually one kind of easier or easiest way to approach these, but that changes for problem to problem. So sometimes these take a little bit of creativity, a little bit of trial and error, and that's normal. That's to be expected. So with these equations, the first thing that I notice is that the left-hand sides of all of these equations are almost the same, right? Each one of these has two of the variables out of the three, but not all three. If we could make them all equal the same thing, we could set them equal to each other and then go do something with that. So if I can get this to, nope, sorry. There we go. Okay, so notice the left-hand sides of the equations are only one variable off from each other. Multiply each by their missing variable so we can equate. So this first left-hand side is missing an x, so I'm going to multiply the whole equation by x. Next one's missing y, so whole thing times y, and then last one, whole thing times z. So if we come out on the other end of this, so we're going to have xyz equals lambda, I'll multiply the x in, so 2xz plus xy. Second one, xyz equals lambda 2yz plus xy. Third one, xyz equals lambda 2xz plus 2yz. Now, each of these equations are equal to the same thing, so we can set them equal to each other, and we can use those to try to solve for x's, y's, and z's. So one thing I want to point out before we go any further with our algebraic steps is we are going to notice that lambda cannot be equal to 0 in this case. So if lambda is equal to 0, so like right here, then that means that xz, yz, and xy would all be equal to 0. But the constraint says that 2xz plus 2yz plus xy must be equal to 12. So we cannot have a case where all of these are 0. So lambda cannot be 0. Okay, so why does that matter? Well, because as soon as we set these equal to each other, I'm going to want to get rid of that lambda and divide it away. But we can only do that if we know that it's not 0. Because if lambda could be 0, then we could be making an algebraic error. So I want to give these functions some labels here so that we don't have to keep copying them down over and over again when we're referring to them. The constraint, I'm going to call this equation 1, and then each of these I'm going to call equation 2, 3, and 4. This is not something you have to do in a bunch of problems, but it definitely will save us time over rewriting these over and over again. Now, because lambda is not equal to 0, so we can consider equations 2 and 3. So if we go ahead and equate them, so we get lambda 2xz plus xy equals lambda 2yz plus xy. We can divide away the lambda now, because again, it cannot be 0. So we have 2xz plus xy equals 2yz plus xy. Subtract off the xy's, they cancel. So we're left with 2xz equals 2yz. And then we can divide away the 2. We're also going to go ahead and divide away the z, because z can also not be 0. If it is, then we're not working with a maximum volume, because volume would be 0. So we're just left with x equals y. So we get x equals y. Now, this didn't give us any specific values yet, but it did give us a relationship. So now if we figure out what one of those two things are, we'll figure out what the other one is. So next up, we will consider 3 and 4. So similarly, I'll just divide the lambdas away right away this time. So we get 2yz plus xy equals 2xz plus 2yz. We can this time subtract away the 2yz's. So we're left with xy equals 2xz. And we can go ahead and divide away the x's just like we did with the z up above. So we're left with y equals 2z. So this is giving us a definitive relationship. So x equals y equals 2z. And now we can go ahead and substitute these values into the constraint. So if you get down to this point of the problem and you're not sure where to go next, if you haven't used the constraint yet, you will need to use it at some point, because that's the whole purpose of these problems, is solving with respect to a constraint. So we need to substitute in to this equation here. We need to put them all in terms of one variable. It doesn't matter which one. I'm going to put them in terms of z, just so I don't have to get like 1/2 in there. So x and y will both be replaced with 2z. So that's going to give us 2 times 2z times z. Plus 2 times 2z times z. Plus 2z times 2z equals 12. So that's 4z squared plus 4z squared plus 4z squared equals 12. 12z squared equals 12. So z equals 1. Right? And again, theoretically, it would be plus or minus 1, but in the context of the side length of a box, we can't have a negative, so it's just positive. And since z is 1 and x and y are 2z, that means x and y are both 2. So our values x, y, and z are here, and we are trying to find the maximum volume of this box. So we're going to multiply. So maximum volume is, so we get 2 times 1, which is 4, is 4 cubic meters. And if we refer back to the last time we did this example, we got it right there. Maximum volume of 4 cubic meters. So this is the method of Lagrange multipliers. So in some cases, like with this one, we were able to solve this problem using the more traditional format of the second derivatives test. But that one required a pretty heavy load to try to compute the partial derivatives using quotient rule, stuff like that. Required a lot of work. This one, it took up a good amount of space, but the level of work that we completed was not too bad. So we're going to see some examples coming up here where, again, we're going to definitely want to utilize the Lagrange multiplier method. So next up, find the extreme values of the function f of xy equals x squared plus 2y squared on the circle x squared plus y squared equals 1. All right, so for our setup, we're going to take grad f equals lambda grad g, and g of xy equals k. So remember with these gradient vectors, right, this is fx, fy, fz equals lambda gx, gy. Actually, no z this time. It'd just be fx and fy equals lambda gx and gy, like that. So we'll do similarly to what we did last time. We're going to equate the corresponding pieces. So we'll have fx equals lambda gx, fy equals lambda gy, and the constraint is x squared plus y squared equals 1. And again, you can always tell what the constraint is because it's the one set equal to a number, equal to a constant. So let's go ahead and set up these equations. So fx is 2x, gx is going to be also 2x, so that's 2x times lambda. Fy is 4y, gy is 2y times lambda, and then x squared plus y squared equals 1 is still our constraint. Now if we look at the first equation here, this gives us only two possibilities. Don't divide everything by 2x. That might be the temptation, but that's not going to give us all the solutions that we need. Instead, subtract, so 2x minus 2x lambda equals 0, and factor out the 2x. So we get x equals 0 or lambda equals 1 for our two possibilities. If you divide away the 2x, you lose this one entirely. So you cut down your solutions in half or even more. So these are the possible outcomes of the first one. So now let's look at the implications of that. What does that mean? So if x equals 0, And we look at the constraint here. If x is 0, then y squared equals 1. So y would be equal to plus or minus 1. Okay, and we can have negatives now because we're not dealing with like a contextual example. And if lambda equals 1, then we look at this equation. If lambda is 1 here, then 4y equals 2y. And there's only one number that if you take 4 times the number and 2 times the number, that they are equal. And that number is 0. So y would have to be 0. So we would get x is plus or minus 1, again, from the constraint. If y is 0, we get x squared equals 1. So x is plus or minus 1. So this tells us, so f has possible extreme values. So this will be 0, 1, and 0, -1. That's this pair right here. Then we have the x's, so 1, 0, and -1, 0. We don't mix and match with each other. So it's these cases or these cases. It's not a combination of just all of them, okay? Because these are two distinct outcomes. So we get only 4 critical points here. Then if we evaluate, so we get f of 0, 1, that's 2. F of 0, -1 is 2 also. F of 1, 0 is 1. And f of -1, 0 is also 1. So we plugged those back into the original function to see their outputs. And remember, with the Lagrange multiplier test, whatever value is the highest, that's the max. Whatever value is the lowest, that's the min. And they can share the title. So in this case, we have 2 values that are the highest and 2 that are the lowest. So we can say, therefore, the maximum value of f on the circle x squared plus y squared equals 1 is f of 0, 1 equals f of 0, -1 equals 2. And the minimum value is f of 1, 0 and f of -1, 0, which equal 1. So we end up getting 2 shared maximum values and 2 shared minimum values. Now I want to take a look at this function graphically so we can see what this actually looks like. Okay. So here's our function. So you can see it's like an elliptic paraboloid, and there's the circle down there on the bottom. So we're looking for the values of the function that are maximum and minimum that also lie on the circle. So if I extend this circle into 3D, you can see how it kind of cuts through and creates this curve along the surface, because the surface isn't perfectly circular, so it's stretching in one direction. So the curve that leaves is right there. So I'll turn that off. So that's the curve that it leaves, and we were finding the maximum and minimum values on this curve is what we were just doing. And as you can see, there's 2 that are symmetric on that side and 2 that are symmetric on this side. You can see 2 maximum values, 2 minimum values, Let me just turn those on, and you can see them right there. So you've got the two maxes up there at the top, the two mins down there at the bottom. So again, this makes no claims about maximum and minimum values on the entire function. This function does have a minimum on its whole part down at the origin. It has no maximum in its entirety, but subject to the constraint, the restriction that is the circle, it does have max and min values, as seen there. All right, let's take a look at one final example. So one final example for the whole chapter. Find the points on the sphere x squared plus y squared plus z squared equals 4 that are closest to and farthest from the point 3, 1, negative 1. Okay, so we're finding points closest to and farthest from the given point. And again, it should be noted that we are dealing with a constraint or a restriction, because if we're just trying to find closest and farthest points, there is no restriction in general, right? If I say, here's a point, find the point that's farthest from it, it would keep going forever and never stop. So we're only looking at points on the sphere. Okay, sphere centered at the origin of radius 2. So when we say that we want to find the points closest to and farthest from this point, we didn't specifically state maximum and minimum in this problem, but it's implied, and we need to figure out what it is saying. What we are trying to maximize and minimize is the distance to the point 3, 1, negative 1. We're trying to maximize or minimize the distance between this point and this sphere. So we would set up the equation d for distance, and we would use the distance formula. So that's the square root of x minus 3 squared plus y minus 1 squared plus z plus 1, right, minus negative 1 squared. But I want to do something a little out of left field here. I want to go ahead and square both sides of this. So in doing so, we get d squared equals all these terms on the right, but with no square root on them. Now, we have to kind of take a logical leap together here. We need to understand that any values of x, y, and z that solve this equation are exactly the same x, y, and z values that would solve this equation. Okay, so, right, if you plugged in any value for x, y, and z over here, if it made this the largest it can possibly be, if it maximized this distance, it's also going to maximize this one, right? Because if I take a number and square it, if the original number was the largest, its square will also be the largest. And similarly, if we are minimizing d, if this is the smallest it can be, then the square will also be the smallest it can be. So we want to maximize and minimize this function, but this one has exactly the same solutions as the other, and the algebra is easier on this one because it doesn't have a square root. So this is not like a mandatory step on these types of problems, but this is definitely going to help us to get rid of this square root. So we're going to work with this equation instead of this one. So these equations have the same solutions, but the algebra is easier on d squared. So f of x, y, z, our function in this case, will be equal to x minus 3 squared plus y minus 1 squared plus z plus 1 squared. And I'll actually go ahead and move that over a little bit. And our constraint, g of x, y, z, is, again, it's the sphere. One, because that's where all the points have to lie that we're testing, and because it's equal to a constant. So yeah, that's x squared plus y squared plus z squared equals 4. Right. So, using the method of Lagrange multipliers, we need fx equals lambda gx, fy equals lambda gy, etc., etc. So for fx, that's going to be 2 times x minus 3 equals lambda times 2x. For fy, we get 2 times y minus 1 equals lambda times 2y. And we get 2z plus 1 equals lambda times 2z. So we have our 3 equations from the gradient vectors, and we have our constraint. So we've got 4 equations to work with, and we need to start solving for x, y, and z values. Now, again, there's not necessarily only one way to solve each of these problems, but there's definitely going to be an easier way. In this case, I want us to notice that this equation is in terms of x and lambda, this equation is in terms of y and lambda, and this equation is in terms of z and lambda. So they're all only one variable and lambda. What we could do is we could go ahead and put each of these variables in terms of lambda, and then we could put everything in terms of lambda, solve for lambda, and then get the x, y, and z. So we're going to solve each for x, y, z in terms of lambda. So we haven't really used lambda that much today so far. Like I said, some examples we won't use it at all. We might overlook it. Other examples it will become a vital piece. So what that gives us here, if we kind of move things around a little bit, so we've got 2x minus 6 equals 2x lambda. So we've got 2x minus 6 minus 2x lambda. Move the 6 over. Oops. Equals 0. Move the 6 over and factor. So we get 2x times 1 minus lambda equals 6. Divide by the 2, so that makes that a 3, and then divide by 1 minus lambda. So we get x equals 3 over 1 minus lambda. So that would be x. And we would do the same thing for y and z. They work out remarkably similarly. So similarly, if we solve for y, we get 1 over 1 minus lambda. And z, we get negative 1 over 1 minus lambda. So we took our 3 equations from the partial derivatives, and we got x, y, and z all in terms of lambda. And now we come to the point where we haven't used our constraint yet. So we can go ahead and use the constraint, substitute in x, y, and z into here in terms of lambda. So sub into the constraint. So we're going to get 3 over 1 minus lambda squared plus 1 over 1 minus lambda squared plus negative 1 over 1 minus lambda squared equals 4. If we square everything out, multiply everything through by 1 minus lambda to clear out these denominators, we end up getting 1 minus lambda squared equals 11 over 4. Okay, because that gives us 9, 1, and 1. So that's the 11. This multiplies over, divide the 4 under. So a little bit of algebra I'm skipping over for the sake of time. Take the square root of both sides. We get 1 minus lambda equals plus or minus rad 11 over 2. Okay, I took the square root of the 4 already. So move the stuff around a little bit to isolate lambda. So we get lambda equals 1 plus or minus rad 11 over 2. So this is our value for lambda. Now we can plug that back in to each of these equations to get the x, the y, and the z. So sub back in to get x, y, z. So there are two solutions here. There's the plus case and then there's the minus case. So what we would do, I'll show one of these. So x equals 3 over 1 minus 1, I'll do the minus case first. 1 minus rad 11 over 2. 1 minus 1 cancels. Negative, negative. So this is 3 over rad 11 over 2. Multiplied by the reciprocal, we get 6 over rad 11. Do that for y and z also. So we end up getting the point 6 over rad 11, 2 over rad 11, and negative 2 over rad 11. And if we substitute in the plus case, so if we did x equals 3 over 1 minus 1 plus rad 11 over 2, we end up just getting the exact opposite. So we get negative 6 over rad 11, negative 2 over rad 11, and positive 2 over rad 11. So we get these 2 points. And the question is, which one of them is the maximum and which one is the minimum? So we would check this in either f, right, which is d squared, or you could check it in d, like in the distance formula. But we end up seeing, so we can show that f of this point has a smaller value than f of this point. So we were trying to maximize and minimize distance. So the first is the min, and the second, the max. So f of this point gives us a smaller value than f of this point. So that means the minimum distance is the first one, the maximum distance is the second one. So thus, gotta love a good copy-paste feature on here. So thus, this point is the point closest to 3, 1, negative 1. And this point is the point farthest from 3, 1, -1. And again, this is on the sphere. Okay, so of all the points on the sphere, we have here the closest and the farthest from the point 3, 1, -1, which hopefully makes sense that they're on exact opposite sides of the sphere, because that's how you would maximize the distance across the sphere, right? You go the whole radius across, and then go, actually the whole diameter across, right? Take the radius twice. And that gives us our maximum and our minimum using the method of Lagrange multipliers. And that brings us to the end of chapter 14 and to the end of our conversation introducing us to functions of several variables, partial derivatives, directional derivatives and the gradient, and now maximum and minimum values using different methods. So that is it for the chapter, and I will talk to you all very soon.